You are listening to The Vocal Technologist. Spoken tech for your ears.
You know, I spent, I think, half an hour yesterday just watching a simple CI/CD pipeline spin its wheels.
Oh, no.
Yeah, waiting for a dependency cache to hydrate for, what, the 5th time this week?
It's those little things.
It is. It's those small, repetitive performance hits that are costing the industry billions. It's the perfect reminder that in infrastructure, if you're standing still,
Yeah,
you're actually falling backward.
you're so right. And that need to optimize, to get rid of those friction points, it's now accelerating at a speed we just haven't seen before.
And it's all being driven by AI, right?
Almost entirely. It's the relentless demands of large-scale AI.
Absolutely. Well, welcome to Tech Tuesdays. We've pulled together an amazing stack of technical briefings, some reports, deep analyses, really covering everything from global internet traffic shifts to critical security threats.
And some really practical strategies engineers are using right now to get that operational efficiency.
Exactly. Our mission here is simple: to synthesize all of this and hand you, the listener, the crucial insights.
So you can be instantly well-informed, ready for the week.
Yeah, exactly. It's time for us to get into the nuts and bolts here on The Vocal Technologist.
Let's do it. I think we should start with the macro view. The data from the 2025 Cloudflare Radar Year in Review, it really sets the stage for everything else.
Okay, so hit me with it. What's the big number?
Internet traffic grew by 19% last year.
19%. That is a massive jump. Honestly, that growth rate alone should be causing some panic in infrastructure teams just rethinking capacity planning.
It should be. But here's where it gets really interesting. It's the breakdown of that traffic. The bots. The bots are the real story.
Right.
Googlebot is still the good faith paymouth, obviously. But what Cloudflare noted was the aggressive nature of AI crawling.
Aggressive how?
They specifically called out extreme crawl-to-refer ratios.
Okay, help me unpack that ratio. What does extreme actually mean for, say, the person running a website?
It means these AI crawlers, the ones feeding all the different LLMs,
Yeah.
they're ravenous.
So they're just taking data.
Constantly. They're fetching data at a rate we've never seen. But, and this is the key, they are not sending any traffic back to the source.
So it's not a reciprocal relationship.
Not at all. It's a massive one-way extraction of resources. And this sheer appetite for training data is becoming a fundamental stress test on, well, global internet resources. It demands immediate action on caching and rate limiting from literally everyone running a service.
It just changes the whole risk profile of running web infrastructure, like, overnight. Okay. Switching gears, though, to a surprisingly positive security milestone from that same report.
Right.
We've actually had a huge win in preparing for future threats, haven't we?
We really have. Approximately half of all human web traffic is now secured by post-quantum encryption.
Wow. Half.
Half. That's a massive operational achievement.
Yeah.
We're moving from a theoretical vulnerability, the risk of quantum computers cracking our crypto, to a practical, large-scale deployment to defend against it now.
That's amazing progress. Really a sign of proactive engineering at a huge scale. And one last detail from the report that I think speaks to our efficiency theme.
The Go clients.
Yeah, the adoption of Go-based API clients exceeded 20%.
That is significant. It shows this continuing shift toward languages that are really optimized for performance in concurrent cloud environments.
Which connects perfectly to the broader picture of AI in 2025.
It does, because that year was really defined by a fundamental shift in the model capability itself.
Right, so it wasn't just about better prediction anymore. It was about models driven by, what was the term? Reasoning?
Exactly, reasoning.
So what does that look like in, like, a real development workflow?
It meant the emergence of truly practical functioning agents. We saw coding agents and CLI workflows that could finally execute longer autonomous tasks.
So instead of just auto-completing a few lines of code.
They were completing entire multi-step pipelines.
Yeah.
The complexity threshold they could handle just jumped dramatically.
So the tool got a lot sharper. But, you know, widespread adoption always comes with a dark side. What new risks went mainstream right alongside these advanced agents?
Well, we saw an immediate escalation of safety concerns. Widespread use of AI browsers, the ability for models to do complex, unmonitored tasks. It led to new challenges.
The YOLO usage stuff.
Exactly, what people are calling YOLO usage. You only look once. Actions that have these rapid, unintended consequences. And, of course, prompt injection attacks were a persistent and, frankly, growing threat.
Because the bad actors learned how to trick the reasoning models into doing malicious things.
Precisely. The moment the models became truly useful, the attack surface just expanded to meet it.
And the market changed too.
Oh yeah, the market dynamics shifted completely. OpenAI's lead, it noticeably narrowed as Gemini advanced. Suddenly we had a true two-way heavyweight fight.
And what about the open weight models?
Simultaneously, Chinese open-weight models just surged onto the scene, making the whole competitive landscape far more diverse. And crucially, the gap between cloud models and local models, it widened even further.
Which confirms that brute force scale and compute power still rule the intelligence curve.
For now, yes.
And since we're talking infrastructure, we can't ignore the operational footprint. The societal impact of this AI explosion became very visible.
Very. On the content side, you have the sheer volume of low-quality AI-generated content.
Like AI slop.
AI slop, as the internet so perfectly dubbed it. It just saturated platforms. But
Yeah.
operationally, we saw a genuine public backlash against data center expansion.
Right, because the energy demands, the land use, they're no longer abstract concepts.
They are highly visible public issues affecting local power grids and, water supplies.
That context sets the stage perfectly for the urgent security alert we need to talk about next.
It really does.
Because while we're dealing with this massive abstract threat of AI resource consumption, there's a very concrete, immediate threat that could take down thousands of existing databases.
We're talking about a digital house on fire.
We are. So, MongoBleed, officially labeled CVE 2025 1P847.
And it is a critical flaw in MongoDB.
Yep.
That is, well, it's astonishingly simple for an attacker to leverage.
So tell us about the mechanism, but more importantly, the impact.
Okay, so the mechanism lives deep inside MongoDB's lib1 message compression path. It's pretty obscure.
But the impact.
The impact is what should be keeping everyone up at night. The flaw allows unauthenticated attackers to read arbitrary heap memory.
Unauthenticated.
Unauthenticated.
Zero credentials needed. That's terrifying.
Yeah.
Define arbitrary heap memory for us. What exactly is an attacker potentially stealing here?
They're essentially peering right into the server's short-term memory.
Wow.
So arbitrary heap memory can include sensitive data that was recently processed, like database credentials, session tokens, internal connection strings.
Even pieces of sensitive user data.
Exactly, if it was just handled. The attacker doesn't need a key or passwords. They just send a specially crafted request, and it triggers this memory dump.
That's why they're calling it a dead simple exploit.
That simple.
And the scope of this is what really ramps up the urgency. This isn't a new bug, is it?
No, and that's the chilling part. This vulnerability has existed in most versions of MongoDB since 2017.
Since 2017.
Yes. And while a patch is out for currently supported versions, the scope of legacy installations it's enormous. Over 213,000 internet-exposed MongoDB databases currently remain vulnerable.
That's a staggering liability just floating out there.
It is. If you're managing MongoDB, you have to patch this immediately, or you are just handing over the keys to your internal memory to any random attacker on the internet.
Take that warning seriously, folks.
Yeah.
That vulnerability reminds us that operational consistency and rigor are they're non-negotiable. Which brings us to how companies are actually achieving that consistency, even in the most complex environments.
Like the edge.
Exactly, the edge.
Yeah, we can talk about the challenge of eliminating what we call snowflake devices.
Those unique, inconsistent deployments that become operational headaches.
Especially in distributed edge AI environments.
So let's look at this case study, the agricultural tech startup, Aurea Imaging. They're managing remote sensing devices spread across fields globally. That sounds like a nightmare to update. How did they solve it?
So Aurea Imaging manages a global fleet of these NVIDIA Jetson-powered devices. And you're right, the complexity of guaranteeing a perfect system update on a remote device, avoiding partial updates or dependency hell, it's immense.
But what was the solution?
Their brilliant solution was to adopt a cloud-native OS management strategy. They used K3s for orchestration and the CNCF Kairos project for the operating system itself.
Okay, Kairos. What made Kairos the key differentiator here?
Kairos gave them atomic image-based OS upgrades.
Atomic and image-based.
Yes, it means the entire operating system and its configuration are packaged and managed exactly like a container image. So when they push an update, it's all or nothing.
So you either get the guaranteed perfect new state or you stay on the guaranteed perfect old state.
Precisely. And that immediately eliminated the inconsistency of those snowflake devices. It drastically improved their operational efficiency and, of course, their security.
That is a huge shift, managing the whole OS lifecycle as part of an immutable infrastructure pipeline. But I do wonder, does that approach scale easily for smaller teams? Without dedicated cloud expertise, doesn't the initial setup get inherently more complex?
It does add some front-loaded complexity,
Yeah.
absolutely. But it dramatically reduces the maintenance burden, which is where most teams spend their time and their money.
That makes sense.
For small teams, using a lightweight Kubernetes distro like K3s alongside Kairos makes the whole thing really approachable. And it pays off immediately by just eliminating all that manual troubleshooting time you get with remote hardware drift.
That makes perfect sense. Okay, let's move into broader cloud infrastructure, specifically scaling MLOps. What are the principles for effective MLOps observability on, say, Amazon EKS? Standard metrics just don't cut it anymore, do they?
Not at all. Standard metrics are the baseline, of course. You still have Prometheus, Grafana, Kubernetes autoscaling. Those are your core scaling tools.
Yeah.
But MLOps demands specialization
Why?
because the bottlenecks aren't in standard CPU usage anymore. They're often deep in the hardware acceleration layers.
So you need deeper visibility into the hardware itself.
Exactly. You need detailed guidance on monitoring hardware specific to ML. So utilization, temperature, performance of dedicated GPUs, AWS accelerators, all of that.
And you need ML-specific metrics, too.
Right. Things that track training throughput, inference latency per model, data loading efficiency. That level of detail is the only way to understand and eliminate the bottlenecks in the pipeline.
Which directly translates to compute cost.
Directly.
And speaking of optimizing compute cost, we have to talk about infrastructure deployment speed. Provisioning can just grind to a halt if teams don't properly manage their Terraform parallelism.
Yeah, what's fascinating here is how parallelism, the ability to run concurrent resource operations, how much it affects deployment speed.
It's a double-edged sword, right?
It is. If you have too little parallelism, your deployment just crawls. But if you have too much, you hit rate limits on cloud APIs, or you accidentally create resource dependencies that cause failures.
So it's a really tight optimization curve.
It is. Configuring and managing that parallelism is just essential to optimize your deployment time. It's not just about Terraform's internal execution, it's about sequencing the interactions with the cloud providers to maximize concurrency without hitting those quotas.
Because provisioning speed is developer velocity.
And developer velocity is business agility.
That optimization mindset leads us perfectly into our next segment, which is the intense pressure on performance driven by cost, by efficient code, and the increasingly finite nature of physical chips.
This is where the financial pressures intersect kind of brutally with engineering reality. The cost of running observability platforms is often just exorbitant.
It is.
Zendesk engineers recently showed how they successfully flattened that massive spend while maintaining performance visibility.
That's the dream. How did they do it? How do you cut the observability bill without losing the ability to diagnose problems?
They used 4 key strategies.
Right.
First, a rigorous audit of all their metrics, traces, and logs, just cutting out the noise they didn't actually use.
Makes sense.
Second, they moved toward adopting single-span tracing.
Okay, define single-span tracing for me.
So instead of collecting and storing every minute detail, every single function call across every microservice, which is crazy extensive,
Right.
they targeted their sampling. They focused tracing efforts only on the critical paths that gave them the most actionable insight. They stopped paying the, quote, observability tax for data they never even looked at.
Smart. What were the other two?
Third was more targeted sampling of data streams, and finally, aggressive log deduplication to get rid of all those repeated redundant log messages. It's a masterclass in treating observability data as a cost center that requires ruthless efficiency.
And that efficiency also applies directly to running the AI workloads themselves, right?
Yeah.
Especially high-performance ML on EKS. We know caching is king here. Data loading is often the biggest bottleneck.
Oh, absolutely. When you're scaling AML workloads, you have to optimize at every single layer. Container image caching, data loading, model checkpointing. Standard storage just can't keep up.
So what are the specialized tools they're using to get around that I/O bottleneck?
They're leveraging services designed specifically for high-throughput, low-latency data access. Things like Amazon S3 Express One Zone and FSX for Lustre.
So these aren't just faster file systems.
No, they are foundational infrastructure choices. They are necessary to ensure that those incredibly expensive GPUs and accelerators are never sitting idle, just waiting for data.
Because if you can't feed the chips.
You're wasting money, period.
And this brings us to that surprisingly profound conclusion about modern programming, the idea that software takes away faster than hardware giveth.
Yeah, and this raises a really important question. Why are C++ and Rust the fastest growing major languages right now? It's not just a passing trend.
It's because computing is getting constrained.
It's constrained by power and by physical chips. Moore's law is running out of steam in a practical sense, especially when you factor in power consumption.
It's the physics of computing forcing our hand.
Exactly. As AI workloads escalate demand, efficiency becomes paramount. So performance per watt and performance per transistor are now critical engineering concerns.
Which drives developers back toward languages that offer that bare metal control and minimal runtime overhead.
It's a return to fundamentals, driven by economics and physics.
Fascinating. Okay, let's wrap up our look at infrastructure updates with a quick kernel on Kubernetes scheduling. What's new in v1.35?
Kubernetes 1.35 brought some significant workload-aware scheduling improvements, which is critical for complex jobs like parallel ML training.
What's the key takeaway?
The key takeaway is the introduction of the new Workload API. It's found at scheduling.k8s.iov1 alpha 1.
And what does that new API let us do?
It lets you define multi-pod application requirements, which is essential for complex, tightly coupled workloads. And more importantly, it features the initial implementation of gang scheduling.
Gang scheduling. That sounds serious. What problem does it solve in practice?
It solves the resource deadlock problem. In the past, if a job needed, say, 3 resources, but the cluster could only place 2.
The third pod would just sit there pending forever.
Right, wasting the 2 that were already allocated.
Uh-huh.
Gang scheduling ensures an all-or-nothing placement. Either all 3 related pods are placed simultaneously or none are,
Which prevents those partial deployments.
drastically improving resource utilization and job completion reliability for complex parallel processes.
That's a huge step for stability in high-demand clusters. Okay, so what does this all mean when we put the pieces together? We've covered the global AI evolution, the immediate danger of MongoBleed, and these complex engineering moves to optimize infrastructure. From the edge with Kairos to the cloud with specialized MLOps toolkits.
I think the main lesson here is that infrastructure now demands hyper-efficiency at every single layer. The security vulnerabilities remind us that consistency is really the only reliable defense.
Right.
And the engineering moves, whether it's single-span tracing or using Rust, they show that AI's demand for compute is forcing an industry-wide pivot toward raw performance efficiency in both code and in operations.
Absolutely. And that relentless pressure leads us to our final provocative thought for you to consider as you go back to your own projects. Given that AI agents are now helping write and synthesize code, and given the aggressive growth of efficiency-focused languages like C++ and Rust because of hardware constraints, will the next generation of application developers prioritize pure efficiency, that performance per watt, over developer velocity?
Yeah, will the goal shift from ship quickly to ship lean and fast? It suggests the future of software development might be less about which framework is easiest to use,
and more about which language can squeeze the absolute last bit of performance out of every single transistor.
It's a fundamental tension, and it's one that's going to shape the next decade of technology.
It absolutely will. Thank you for joining us for this in-depth look at the infrastructure landscape. We really hope this knowledge gives you the edge you need for the week ahead.
Until next time.
Spoken Tech for your ears.